Welcome students. Welcome to today's session of ALPHORES e-learning program. In this session, we will discuss about some numerical applications of thermal stress. Before going to the numerical applications, let us have a quick review about the formulae involved here. As we explained with the previous classes, thermal stress is the stress developed which prevents the expansion of a solid body like a metallic rod when it is fixed between two rigid ends. When it is fixed between two ends, suppose this is one fixed end and there is the rod is fixed at the other end also. If L is the length of this rod, alpha coefficient of linear expansion, then when the temperature of this rod is increased by delta T, we said there should be an expansion, but to prevent the expansion, these rigid fixed ends, they will be applying a force on it. Because of that force, we have calculated the stress, and thermal stress we have calculated is given by the equation thermal stress equal to force by area. It is Y alpha delta T. And if you calculate the thermal force is Ya alpha delta T. So this is the thermal force and this is the thermal stress. Stress you are measuring as force per unit area, that is Y alpha delta T. It depends upon Young's modulus, coefficient of linear expansion, delta T, the change in the temperature. And coming to the force Ya alpha delta T, where A is the area of cross section. And clearly, if the area of cross section, when you calculate for a circular cylindrical rod, cross section is a circular, then if R is the radius, this Y we can write as pi R square, that is the area of cross section, into alpha into delta T. So these are the basic formulae, but when we are applying, how to apply? You know, physics is basically an application oriented subject. Knowing the equation is very simple. Yeah, all the problems related to the thermal stress we can solve only by using these two formulae. But how to apply, we have to learn by knowing the numericals. Learning through numericals, that is the easiest way. So let us try to apply these equations in the given cases, how to solve it. Right? Now let me take only these two equations on the board, so that we can know how to apply. So the first equation is thermal stress, that is force by area, is Y alpha delta T. And if you calculate the thermal force, force is Ya alpha delta T, or if it is circular cross section, we can also say pi R square alpha delta T. Now let us go ahead with some numericals. Let us consider two materials, two rods. There are two rods of different materials having their coefficient of expansion in the ratio 2:3. The coefficient of expansion is in the ratio 2:3. Young's moduli, they are in the ratio 3:2. Young's moduli are in the ratio 3:2. Now let us suppose they have their thickness, let us say they have same area of cross section. When they are subjected to same change of temperature, I want the ratio of thermal stress developed. Now when we ask this problem, finally what we have to calculate? Ratio of thermal stress. Ratio of the thermal stress I want to calculate. Now because we have to find out the ratio of thermal stress, let us look at the formula for thermal stress. F by A, that is Y alpha delta T. So what are variables in this problem? Young's modulus is variable, coefficient of linear expansion, and delta T, change in temperature. But in our problem, coming to the equation of the stress force by area, that is Y alpha delta T, for both the rods, if you consider coefficient of linear expansion is different, Y is different, alpha is also different. but delta T is the same. Delta T is the same because both are subjected to same change of temperature. So very clearly, when you are in this formula for stress, we know delta T is the same for both of them. Delta T is the same for both of them. So simply the stress is proportional to y into alpha. Therefore, you can straight away take the equation stress in the first one divided by stress in the second one. That will be equal to, because it is proportional to y into alpha, it is y1 by y2 into alpha 1 by alpha 2. So, how we arriving at this equation? Because in the given problem, what is asked is thermal stress. So, when you are talking about thermal stress, what is the basic equation for thermal stress? Y alpha delta T. But now, let us apply this equation for our problem. What is the data given here? Young's modulus is different, coefficient of linear expansion is different, but delta T is not the same. Delta T is the change in temperature, it is given as the same value. So delta T is the same for both of them. So very clearly in this equation, because delta T is a constant, the thermal stress is proportional to the product of y and alpha, or F by A is proportional to y into alpha, or the ratio of the stresses, it is y1 by y2 into alpha 1 by alpha 2. So the ratio of the stresses is, ratio of y1 by y2 is 3:2 and alpha 1 by alpha 2, that is 2:3. What is the final answer? 1. They are having the ratio, same stress in both the cases. So how we are applying, and first after reading the problem, try to identify what are the variables in the problem. And what we have to find out, find out the variables, then think of the formula related to that. Straight away after reading the problem, we cannot go for the direct formula, right? So first let us understand the problem, what is happening, what are the variables, what is to be calculated, then you can think of what is the relation between them. Automatically we can solve the problem in this case. So very clearly, because the stress is proportional to y into alpha, stress in the first rod divided by stress in the second rod, the ratio is y1 by y2 into alpha 1 by alpha 2. So y1 by y2, the Young's modulus ratio is 3:2 and alpha ratio 2:3, the ratio becomes 1, which indicate that the thermal stress is same in both the rods. Now let us go ahead with another model with the same data. Now let us consider the two rods. They are having their coefficient of linear expansion 2:3 ratio, Young's modulus 3:2. Let us suppose area of cross section is same for both of them. Now let us suppose, let us make a small change here. Their coefficient of linear expansion is in the ratio 1:2. Ratio is 1:2. Young's modulus is 3:2. Now area is the same. Now I want for the first rod delta T1 is the change in temperature. For the second rod delta T2 is the change in temperature for the second rod. Now what I want is delta T2 is given as 100 degrees centigrade. Delta T2 is given as 100 degrees centigrade. Now I want the value of delta T1 such that stress produced in the first rod is equal to the stress produced in the second rod. Try to understand. We are taking two rods of coefficient of linear expansion in the ratio 1:2, Young's modulus in the ratio 3:2, but they are having same area of cross section. Now for the second rod, the temperature is increased by 100 degrees centigrade. Now I want change in the temperature of the first rod so that the stress in the first one and the second one are equal. Remember that when we are solving the problems in physics, every problem will be containing a keyword. If we understand that keyword, easily we can solve. What is the keyword here? The stress in both the rods is same. Stress in both the rods is same. So very clearly, what is the equation for the stress here? The stress developed in the rod, we know it is y alpha delta theta. This is the equation for stress. So stress is the same. Stress is the same in both the rods. Then what we can write? What we can say is, in the first one, it is y1, alpha 1 and change in temperature in the first rod. Let us say delta theta 1. That must be equal to, for the second rod. When you are taking the second rod, the corresponding values are y2, alpha 2 and delta theta 2. So because this is the equation for stress, y alpha delta theta. But what is the condition given to us? You have to find out the change in temperature for the first rod such that stress in both the rods is same. So stress must be the same. Let us equalize the stress in both cases. So stress in the first one, y1 alpha 1 delta theta 1 is equal to y2 alpha 2 delta theta 2. Then what we have to find out? We want delta theta 1. Delta theta 1 will be equal to, as per this equation, y2 alpha 2 by y1 alpha 1 multiplied by delta theta 2. So let us substitute here. y2 by y1, the ratio is 2:3. So y2 by y1 is 2:3 into alpha 2 by alpha 1, that is 2:1, and delta theta 2. For the second rod, the increase in temperature is 100. So delta theta 2 is 100. Now let us find out. So very clearly, this is 400 by 3, that is delta theta 1. That will be around 133.33 degrees centigrade. So we say that change in the temperature of the first one is 133, such that stress in the first rod, stress developed in the second rod, both are one and the same. So this is another possibility. A problem can be like this also on thermal stress. So here the alpha ratio is given, Young's modulus ratio is given, but area is the same. Let us suppose area is the same. Now for the second rod, change in temperature is given, and we want change in temperature for the first rod such that stress is the same. So stress is the same is the important point we have to remember. So because the stress is same in both cases, let us take the equation of stress and equalize the stress in both the rods. In the first rod, y1 alpha 1 delta theta 1, second y2 alpha 2 delta theta 2. Now of all these factors, what we don't know is delta theta 1. So take equation for delta theta 1. You will be getting the value, substitute the numerical values, you will get the final answer. So understanding the problem is more important, then easily we can approach for the formula, right? Now let us move on to another possibility of a model problem present on this thermal stress. For two rods, alpha is in the ratio 1:2, Young's modulus is in the ratio 3:2. Suppose the thickness of the rods, let us say R, is in the ratio 1:2. Let me take a different value. The thickness is in the ratio √2:√3. √2:√3. I want the ratio of the thermal stress. I want the ratio of thermal stress corresponding to same change of temperature. Now let us look at the problem once again. I have taken two rods having alpha values in the ratio 1:2, Young's modulus in the ratio 3:2, thickness in the ratio √2:√3, and ratio, I want the ratio of the stress corresponding to same change of temperature. Very clearly change in temperature is same, and we want ratio of the stress. So stress, the ratio we have to calculate under the condition that change in temperature is same for both of them. So in the equation for stress, if you observe the stress, we can write y alpha delta theta, but in the equation stress, delta T is the same. Delta T or delta theta, change in temperature, let us say the change in temperature is delta theta, that is same. Then in this equation, we don't have the equation of the area, simply y into alpha we require. So if the thermal stress is to be calculated ratio, therefore from this equation, as in the previous case, the stress, because corresponding to corresponding to the same change of temperature, delta theta is the same, or we can say the stress is proportional to y into alpha. Therefore, stress in the first one by stress in the second one, that is y1 by y2 into alpha 1 by alpha 2. What is the ratio of Young's modulus? It is 3:2, and ratio of alpha 1:2. So the ratio becomes 3:4. So here, because thermal stress is asked, we need not consider the area, because in the equation of stress y alpha delta theta, only variables are y, Young's modulus, coefficient of linear expansion, and change in temperature. Already it is given that change in temperature is same. So only variables are Young's modulus and coefficient of linear expansion. So we know the relation, because stress is proportional to y into alpha, delta theta is constant. So let us apply S1 by S2. S is the stress I am representing here. So S1 by S2 will be equal to y1 by y2 multiplied by alpha 1 by alpha 2. Take the ratio y1 by y2, Young's modulus in the ratio 3:2, alpha in the ratio 1:2. So the final answer becomes 3:4. Now, in the same case, let us calculate the ratio of thermal force. Let us calculate the ratio of thermal force corresponding to the same change of temperature for the same data. Let us calculate the ratio of thermal force. So far we are discussing about thermal stress. Now let us go ahead with an application for thermal force. When you want to calculate the ratio of thermal force, condition is delta theta is the same. Again, the rods are having coefficient of linear expansion in the ratio 1:2, Young's modulus in the ratio 3:2, thickness in the ratio √2:√3, and I want the ratio of thermal force. So because you are asked about thermal force, let us look at the equation for thermal force. So thermal force is YA alpha delta theta, and because the area of cross section, generally the rods you will take, they are expected to have circular cross section. If the cross section is something different, it will be clearly mentioned in the problem. After this we will go ahead for that also, but it will be mentioned. If anything is not mentioned, simply you can consider that the rod is having a circular cross section. When it is circular cross section, area we can write as pi r square, where r is the radius of the rod, into alpha into delta theta. Now let us look at the problem. In our problem, delta theta is the same. So clearly delta theta you need not consider. When you are calculating the ratio of the force, delta theta, because it is the same, you can leave it. But what are the other factors? Pi is also a constant. Then the variables present in the problem are Young's modulus, the radius of the wire, and coefficient of linear expansion. So as per this equation, what we can write for the value of the force? Very clearly, force is proportional to Young's modulus and radius square and alpha. Because in our problem, delta theta, change in temperature, is found to be the same, and pi is already a constant. So variables are only Young's modulus, radius of the rod, and alpha. So force is proportional to these factors. Now if you take the ratio, it is F1 by F2, that will be equal to alpha 1 by alpha 2 multiplied by y1 by y2, right, into r1 square by r2 square. Now let us check whether these values are available with us or not. We know the coefficient of linear expansion, alpha is in the ratio 1:2, Young's modulus in the ratio 3:2. So these are the data available with us. So let us substitute here. Coefficient of linear expansion, what is the ratio here? 1:2. Alpha is in the ratio 1:2. Young's modulus y1 by y2 ratio is 3:2, and r1 square by r2 square. Remember, when we are solving these problems, thickness, unless it is specified, we should consider as the diameter, because if you consider a cylindrical rod, let me draw here. If you consider a cylindrical rod like this, the diameter represents the thickness. So if thickness is given, you should consider that it is a diameter. But what we want here, r1 square by r2 square, where r is the radius, but diameter, it is the double the radius. So radius and diameter will be having the same ratio. Therefore, in place of r1 square by r2 square, these are the thickness ratio, that is root 2 by root 3 whole square, or it is 2 by 3. Then what is the final answer? This is cancelled, this 2 is also cancelled. Final answer is 1:2. So simply the ratio of the forces, we can say it is 1:2. Right. So we are asked to calculate the force. So depending upon the problem, from the equation of the force, we have found that it is proportional to these factors only. So because the variables are here, what are the variables in the problem is thickness of the rod or radius, coefficient of linear expansion, and the Young's modulus. Let us put it in the equation to get the ratio. Now let us move on to another one. Suppose I am taking two rods of coefficient of linear expansion in the ratio 1:2, Young's modulus in the ratio 2:3, and the rods are having same thickness. They are having same thickness. But first one is having a circular cross section and second one is having a square cross section. First one is having a circular cross section and second one is having a square cross section. And now corresponding to change in temperature having the same value for both of them. For both the rods, change in temperature is same. The alpha ratio is 1:2, Young's modulus 2:3, but they are having same thickness. Corresponding to same change of temperature, I want the ratio of thermal forces developed in the two rods. I want the ratio of the thermal forces, F1 by F2. This factor we have to calculate. Right, let us move on. Force ratio we want. What is the basic equation for force? Force is YA alpha delta theta. Young's modulus, area of cross section, alpha, coefficient of linear expansion, and change in temperature. Now, in this equation, delta T or delta theta or change in temperature is same for both of them. So, delta theta is not a variable in our problem. Delta theta is not a variable because it is same for both the rods. Then what are the remaining variables present here? Young's modulus is a variable, coefficient of linear expansion is variable, and area of cross section is also variable. But here, when you are calculating the area of cross section, we are given a condition. What is that condition? They are having same thickness, but first one is having circular cross section, second one is having square cross section. Then how to get the area? Now, same thickness in the sense, suppose the circular cross section is like this. Cross section, whenever the cross section is, circular cross section is given, the thickness, I told you, it represents the diameter. So, let us say diameter or the thickness is x. Thickness is x. Then, corresponding to this circular cross section, radius becomes equal to x by 2. X by 2. So, area of cross section of the circular rod, which is the first one. So, A1 becomes pi r square, which is nothing but pi x square by 4. Because the thickness is x and thickness, I told you, it represents the diameter. So, radius becomes x by 2. So, as radius is x by 2, area of cross section is, first one is circular cross section. So, A1 equal to pi r square, because x is r by 2 here, sorry, r is x by 2, it is pi x square by 4. Now, taking the second one, we are having a square cross section. But remember, thickness is the same. So, it should also have the same thickness x, but it is a square. So, each side is x only. It is a square of side x. So, the cross section of the second one becomes it is a square. So x square is the area of cross section for the second one. So this part is an important one. Here, because the same thickness is given, for the same thickness for circular rod, diameter is x, so radius becomes x by 2, and correspondingly area of cross section becomes pi x square by 4. And for the second one, area, it is a square cross section of thickness x, so area becomes x square. Therefore, let us apply the equation. As from the equation of the force, we said delta theta is same for both of them. It is not a variable. So very clearly, the only variables present in the problem is F proportional to YA alpha. YA alpha, where Y is Young's modulus, area of cross section, and the coefficient of linear expansion. So take the values F1 by F2, that is Y1 by Y2. Area of cross section, the first one A1 by A2 into alpha 1 by alpha 2. Let us take the values. Y1 by Y2, Young's modulus is in the ratio 2:3. So it is 2:3. Area of cross section A1 by A2 we want. What is A1 here? Pi x square by 4 for circular cross section. Pi x square by 4. And second one is having A2. It is a square cross section of side x. So clearly it is x square into ratio of alpha. Alpha ratio is given as 1:2. So this becomes 1:2. Then what is remaining here? X square factor is cancelled and this 2 factor is also cancelled. Then what is remaining is pi in the numerator and here 3 into 4, 12 in the denominator. So the ratio of thermal forces in the two cases is pi:12. So these are some numerical applications to understand how to apply the basic equation that we know. So knowing the equation is different from application. So in all these problems, I tried to make you understand how to apply. So simply immediately after reading the problem, don't think about what is the formula to solve this problem. First, let us identify what are variables in the problem and what is not a variable, what is to be calculated, and what is actually happening there. Then we will get the basic formulae, because in this topic the only formulae we come across is only 2. So just what are the variables, by finding them you can apply the required equation, and by substituting the numericals given you can easily solve the problems. So make a practice of this and go through this problems one or two times, so that until you can understand how we are applying, try to learn that. Try to learn the procedure, how we are approaching. Understanding a single problem is not sufficient. Understanding the approach is more important. So try for it, and in next class we will go with some more numericals, and with this let us close for today class. Thank you very much.